Okay, let's get started then. So, yeah, in Tuesday's lecture, you learned about cache-oblivious algorithms, and remarkably, there are algorithms that use cache asymptotically optimally, even though they contain no cache parameters, such as cache size or cache line size. And today, I'd like to talk about a couple of applications of cache-oblivious algorithms, focusing on this one in particular, which is simulation of heat diffusion. Now, this is a famous problem that some of you may have seen in a physics or math or material science class, heat diffusion. So let's take a quick poll on how familiar everyone is with this problem. So, we could put that up in the Slack poll. That would be great. Let me look at Slack so I can tell what's going on. Okay. Good, okay. So, don't worry if you're unfamiliar with heat diffusion. I'll explain all the background you need to know about the physics. We're going to focus on the algorithms and the caching, not the physics, but it is nice to derive it from, physics principles. Okay, so only 22 out of our, how many people are with us right now?
46, including
46.
staff. So maybe
Forgot
40 students.
Some lackards, I guess. Okay, we'll move on, but please let me know generally what your level of confidence is. I guess nobody has really coded it or studied it from that point of view. So here's a picture that shows what we want to calculate. You can imagine that there's a flat metal plate that starts out cold, represented by blue in the figure. Okay, so this is a 2D heat equation. Of course, you can do this in 3 dimensions is what people like to do. That's very computationally intensive. So we'll initially look at 2, and then we're going to look at 1, and then we'll come back to 2. So there's a heat source, which is yellow in the middle of the plate. And over time, the heat diffuses through the material. So orange, red, and purple represent some of the intermediate temperatures of different hues. We'd like to simulate the transfer of heat so that from the initial conditions, we can compute a pretty picture like this of the heat transfer. Okay, well, of course, people who do this thing for a living want more than a pretty picture. But honestly, I did choose this problem in part because of the pictures. Now, here's an example of the result of a simulation. We started with the heat pattern on the left, and after running the simulation for a few steps, we obtain the heat pattern on the right. Okay, these are the kinds of things you'd like to be able to run backwards. So you take this and you say, run it backwards, and you come up with 6172. Okay, to simplify our math, we're going to look at the one-dimensional version of the heat equation. Okay, so you can think of this as a bar of metal. Okay, and we're going to assume that there are boundary conditions where there's something holding the temperature at either end at a fixed value. So on the left end of the bar, it's cold. And on the right side, it's hot. Okay, and initially the bar, actually, I guess we don't care what the initial temperature of the bar is, okay? So for some problems, you care about the initial state, but here we're just gonna look at how we get to the steady state. So if you wait long enough, the temperature across the bar stabilizes into a steady state. And that's what we want to compute. So that raises the question of how do you take a differential equation and produce a piece of code that implements it? Okay, so I'm not going to go into the differential equation. You can go to your math or your physics class or material science or whatever, okay? But it's a common problem whether you're doing a wave equation or there are membrane equations and fluid flows, lots of places people want to be able to simulate it. And even in things like games, people often want to do something that will give some realism to what they're doing. And certainly if they're trying to have a lot of time to spend producing a movie or something. Okay, so a common way to transform a partial differential equation to something that you can execute on a digital computer is to use the finite difference method. So let's have another poll. How familiar are you with finite difference approximations?
It seems I've also run out of poll usage for the free tier, so if someone else could.
Can somebody else?
Or teach.
Yeah, I can take over.
Great.
Cool, thanks.
Thank you. That was quick.
I suppose I've also submitted as many polls as Tim, so there's that.
Yep. Well, that just goes to show, right? So did we?
Sorry, I need a sec to pull up this document and get situated.
Okay. Well, in the meantime, I'll move along and then we'll take a look. So, the earliest known use of this method was by the famous Swiss mathematician Leonhard Euler around 1768. So it's a pretty old method. And I'm going to illustrate it for one dimension, but the method generalizes to multiple dimensions. So here's the heat equation in one dimension. Okay, so normally on the right-hand side for multiple dimensions, you have the divergence. So you're computing a Laplacian. Okay, but you don't have to even know what any of those things mean. Okay, so we want to find discrete approximations for the two formulas on either side of the equation. On the left side, we have partial u over partial t, partial u with respect to t, and then we have on the right-hand side alpha times the second partial of u, okay, with respect to x. Okay, so so those are the two places that we want to get a discrete approximation. Okay, no progress yet, eh, Noah? No problem. We'll just keep moving along. Okay, so we can approximate the left-hand side. Okay, so by picking a tiny value delta t. So u of t comma x is the heat at position x at time t. And so the left-hand side is the partial of that. And we can compute that using a standard approximation that you're probably familiar with, which is the approximation of a derivative. We basically take a small, we take a tiny value, delta t, and we compute the slope of the line segment that goes from u of t comma x to u of t plus delta t comma x. And the slope of that is the, what is it? It's the run over the, no, the rise over the run. I think that's what I learned many years ago. Okay. So we take the function, and that's going to be then the difference of those two things. And we take the difference in t between t plus delta t and t, and that's delta t, that goes in the denominator. Okay. And as you, I'm sure know, if we take the limit as delta t goes to 0, that's the definition of the derivative. If we took the limit as t got smaller and smaller, we approach the derivative. But we're going to just use a small value. Okay, so that's the first step. We did the left-hand side. Now we're going to approximate the right-hand side of the heat equation in 2 steps. Okay, because we have to compute the second derivative. So we want to first compute the first derivative and then compute the second derivative. So we do that to compute the first derivative using a similar method, but this time we're going to approximate it using the point t comma x plus delta x over 2 and u of t comma x minus delta x over 2. Okay, now the difference of the x coordinates there is still delta x. So we get a delta x in the denominator, but we've done a little bit of a different thing in the numerator, and that's just going to be convenient for the math. Okay, so that's our approximation of the partial with respect to x. But we need the partial of, we need the second derivative. Okay, and so we can get that. We can get that by now taking the partial of the first derivative. Okay, so the so we get that by essentially take the partial of the first derivative approximation. Okay, and so that's just going to be the derivative with respect to x of the numerator, which has 2 parts, of the previous equation. Okay, and in this, the derivative of delta x itself with respect to x is 1, I think. Okay, so we then can approximate this derivative by taking by using once again the partial of u. So here what we do is we essentially end up adding the terms of the 2 delta x's, because we have a minus delta x, that gives us this delta x. And then the 2 minuses here, we end up with on the right-hand side here as a minus delta x. And then the difference between this is a delta x, so we get another delta x squared. And in the middle here, if you look carefully, what happens is you get them adding up, but the delta x over 2 and the delta x minus delta x over 2 here, okay, you're taking the opposite sign, so they add up to cancel. And so you end up with just 2u of tx over delta x squared. And you can take a look at this on your own, and you can, this is on Wikipedia, this is everywhere. So that's the right-hand side. Okay, so we have the left-hand side approximation, the right-hand side. And so we can reduce that by setting those are supposed to be equal. Okay, so we set the first equation approximation equal to the second equation approximation here, the last equation approximation, sorry. Okay, and that's just this equation. Okay, and that's what we're going to work with. This is something now that's discrete. It's got no derivatives in it. It does have some small values, and we'll see how we're going to deal with that. Okay. So the way we deal with that is we're going to make what's called a 3-point stencil. Okay. And a 3-point stencil is going to update, is basically we're going to have a set of discrete points in X representing the metal bar or whatever it is that we are finding heat on it. The endpoints will be boundary conditions. Okay, so those we're going to keep constant. And there are techniques for changing that as you go, but we're going to just look at a very simple one because we're more interested in the algorithms than we are in all of the ways that the scientists use this. Although you may be interested in that, and it's pretty interesting stuff. Okay. Now, what we're going to do is we're going to iterate through time steps to simulate the flow of heat. Okay, and we're going to update each point in the array based on its own heat and the heat of its neighbors. Okay, except for the boundary points. Okay. So what we're going to do is, what I've drawn here is, although we're going to just do it on the single array, I'm going to draw out the whole iteration space in time t so we can see what's happening from step to step. So you wouldn't ever want to necessarily build out this whole space. This is size nt, okay? And we can update things in place using just size n, okay? So every row represents the bar at a particular time step. Row 0 is filled with the initial conditions. And the simulation updates each point in the space-time grid based on the points below it. Okay. So here's how we do the update. So what we're going to do is simply choose our delta t to be 1 and our delta x to be 1. Okay, in this. So delta x is going to be just the distance between the grid points here. Okay, and if it was a different value, you can just scale things. And in fact, it all ends up in alpha in the end, okay, by having a modified alpha. Okay, now, if we let them both be 1, then the first simplification that we get is that the denominators disappear. They're just 1. Okay. And as I say, if there were a value, we could throw it all into whatever the constant is for alpha. Okay, as you can see, just factor it out, and you'd have alpha. But in any case, this is our current plan. Now, once we've done that and gotten rid of the denominators, on the left-hand side, we can throw the u of t comma x term to the right-hand side, okay? We just add it to both sides, okay? And now we get essentially the update rule at the bottom, okay? So this is code now, okay? So notice that the right-hand side of the assignment that I've made here are 3 values that depend entirely on t, on time t. So that means we can compute the left-hand side, which is a point in the heat state at time t plus 1. Okay, so because all the stuff on the right-hand side is stuff that we already know, and now it tells us what we have at the next step. Okay, so the arrows that I just drew here show how a point on one row depends on the 3 points below it. That's why it's called a 3-point stencil. Okay, and the stencil shape, some people write it as, with those 4 points, you make a tetromino, okay, a domino with four squares in it. Okay, 3 on the bottom and 1 in the middle on the top. And that's our stencil. Okay, so to compute the whole array is easy at this point. We just need a doubly nested loop. Okay, so the outer loop is going to have index t, and the inner loop has index x. Okay, so we're going to go through all the x and then increment t, and then all the x and increment t, and so forth. Okay, so let's look at how we compute row 1 from row 0. Okay, so here's the first point. Okay, we do those calculations. We apply the update rule. Okay, and then once we're there, we move the stencil over 1 and we compute the second point. And then we can go a little bit faster because I think you get the gist until we've computed the whole row. Okay. And now we go ahead and compute row 2 from row 1 in exactly the same way. Okay. And then we can just keep computing each row from the previous. And you can see it finishing up. And I guess we haven't been able to get the poll to work. Is that right? TAs, have we been able to get the poll to work or no? Noah?
Finite difference poll. It should be up.
Oh, it's up. I don't see it here. Oh, there it is. Wait a second. Can you just solve this with convolution? Yes, you can do convolution to solve this. And in fact, there's some quite interesting stuff, okay, that has transpired recently about using convolution to actually compute this quicker, okay? And we have a few people who are confident in finite differences, okay? And some people have not seen finite differences, but some people, maybe they've seen a little bit. Okay, so I think it probably depends upon your background. That would be my guess, is that's mostly a background difference. Okay, thank you. Thanks, Noah. So for a two-dimensional heat equation, okay, then you're going to have a three-dimensional space-time solid, and you're going to get at every point, 1 point on one layer is going to be dependent on 5 points below. Okay, so you get then, I guess, a 6-point stencil. And for three-dimensional heat equation, then each point is going to be dependent on 3 points in each dimension, but the middle point is shared. So I guess you get what? Let's see, you get, no, I'm sorry, you get a 5-point stencil for 2 dimensions. get a 5-point stencil for 2 dimensions. And for 3-dimensional heat equation, you get a 7-point stencil. Okay, and then there are lots of people do stencils for all kinds of things, including for graphics filtering and such. Okay, and as I mentioned, the method of finite differences can be applied to many other problems, such as wave equations, membrane equations, fluid flow, stress and strain mechanics, and so forth. So it's not the only way to solve this kind of problem, okay, but it's one way to solve it, okay? And the general approach is, I think you get the idea of, okay? Now, here's the code. So you can see it's pretty short, okay? The outer, basically it's just put that update into a doubly nested loop. The outer loop, okay, the time loop indexes over time, and the inner loop, the space loop, indexes over space. So the slow moving index is t and the fast moving index is x. And at each point, this code performs the update function by calling the function kernel, which it's requesting the compiler to inline. Okay, because you really don't want to pay for function call overhead when you implement this. Okay. Now the argument to kernel is a pointer to the array element to be updated. Okay. And this function uses a C trick that you've seen before. Okay. So its argument is a pointer W, okay, to the array element that we want to update. Okay. And so, for example, we're giving it a pointer here to the cell that we're trying to update. Okay. For the moment, disregard the mod 2s, and I'll explain that in a minute. Okay. So what it does is it treats the W as an array, and it can access the preceding and following elements by indexing W of -1 and W of +1. Okay, so that's kind of a trick to make it easier to write that code, is using that C trick. Okay, and the code uses one more trick. Okay, so we don't really need to store the whole iteration space, which would take order capital T times capital N storage, order TN storage for the capitals. I'm using the lowercase for the indexes. Maybe that wasn't such a great choice. It's good for a paper. It may not be so good for a lecture. Okay. So, so rather than using the whole iteration space, we're using two arrays, U of 0 and U of 1, and it switches between them. Okay, and it does that by doing mod. Okay, so on even time steps, okay, we update U1 based on values from U0. So it does this. Okay, and then on odd time steps, okay, we update U0 based on values from U1, like this. Okay, so we end up using order n space, not order nt. Okay, so that's two cute tricks. Okay, that was your treat for the trick. So happy Halloween. This is a good time for questions. No, Johnny, you're not going crazy. That was me just having a little fun. So any questions about this right now? So we can take audio or Slack, either one. Any questions? We've got some people typing. Well, if you pass, back in this code, okay, if you pass, whoops, wrong one. Okay, if you pass, so we're passing the address of the index, right? So you could, there's other ways you could express that. This one, though, I think is simple. Okay, because this is an index. Okay, it's the index of u of t mod 2 and x. So if we have these two things, it basically computes, gives you a pointer to exactly that point. Okay. Yeah, there's actually ways you can do the derivation. So somebody, Wan Lin asked, why do we use central finite differences for one side, but normal finite differences for the other? You can actually do this. What a lot of people derive it is they do a forward difference that is, x plus delta x on one side and a backward difference, x minus delta x on the other. And then they combine also the same way. Okay, there are a variety of ways to do this. Okay, I'm not an expert on this calculation. I don't know if you could tell. Okay, I last had a physics class in 1972. 1972 was the last physics class I had. So that's a long time ago. Okay, let's move along here. Okay. So now I want to talk about how this, analyze this from the point of view of cache misses. Okay, so the code is order NT. Okay, it's just a doubly nested loop. Okay, so in order to do the cache oblivious, we're going to go back to the ideal cache model that you were introduced to last time. At least I think most of you were introduced to it last time. Okay, so just recall it's got a 2-level cache hierarchy, and it's got a cache of m bytes. Okay, or in this case, we're actually going to say it's got m. Doesn't matter how you calculate it. We're going to actually say it's got room for m points, and it's got a cache line length, a block size, of b bytes, and it's fully associative. And the formal definition says that you have an optimal omniscient replacement. But you can also, we saw that there was a theorem that said, hey, you can just use LRU and it's going to be the same asymptotics. Okay, so that's your choice. Okay, now, in the ideal cache model, we analyze algorithms using 2 performance measures: the work, which is T, and the cache misses, Q. Oops. Okay, I've got a variable collision. I forgot that I was using capital T to mean the number of time steps. Okay, I think it'll be okay. I don't think we use work T very often, and when it is, I think it'll be clear. Ooh, boy, giving a lecture and having all these variables floating around. It's a tough life as a professor, let me tell you. Okay, so let's take a look at the code. So here's the code again. The slow moving dimension is T and the fast moving dimension is X, as we mentioned. And this code looks pretty good. The accesses, in fact, are contiguous in the fast moving dimension, which means that the code should vectorize and prefetch well. Okay, should be great. But let's look at the cache behavior. Okay, so the illustration that I've just put up shows the space-time iteration space, which has size theta of nt, capital N, capital T. Okay, but the physical memory is that we need is predominantly U. Okay, which is where we're storing the heat values, and that has size order n because it contains only two length n rows, U0 and U1. Okay. Now we're going to analyze this when the number of points in the array is larger than the cache size, because that's the interesting case, right? It's if things are small, they tend to fit in cache, and you might get something in the transition, but generally we're interested in analyzing things to understand scalability. We want to run big problems. And also, let's assume LRU replacement, because that'll let us think a little bit about exactly what the state of the cache is. Okay. So to compute row 1 from row 0, the stencil, which is shown in blue, moves from left to right. Okay. Now we'll only look at the reads, but the writes behave similarly. Okay. So we're only going to look at, as if we need to read things, but the writes behave similarly, and it's just more complicated to do them at the same time. Okay. As the code scans row 0, there's going to be one cache miss for each cache block because there's nothing in the cache to begin with. Okay, maybe there's something in the cache, because it got initialized or something, but we'll presume there's nothing there. But that's okay. That's just n over b cold misses, assuming that b divides n. If it doesn't, then you got to take a ceiling there. Okay. So at the end of row 0, which part of the array U is in the cache? Okay, let's do a poll. Okay, let's do a poll on Slack. So is it, which part is in the cache? Is it the points from the left end of the row, the points from the right end of the row, scattered points across the row, or none, the cache is empty? Wow, that was pretty quick.
I was on top of it this time.
Yep. Well, also students responded quickly. I guess
yes,
this is an easier question than what your familiarity is with the heat equation or whatever. Okay, so the points from the right end of the row. In fact, all the points at the left end of the row have been kicked out at that point, because with LRU, you're always replacing the one that was last used. So the first one to go out is the first one that we computed on. And the second one to go out is the second one we computed on, and so forth. So by the time we get to the end of the row, all of row 0 except the last M over B cache blocks would have been evicted. Now, after reading everything in row 0 to compute row 1, the code starts reading row 1 to compute row 2. Okay? And right off the bat, row 1 gets a capacity miss because the cache is full of stuff on the right end of the row. Okay? And as the code scans to the right, it incurs a capacity miss, okay, for every cache block that it reads, okay, because the cache is full and we have to evict something, and then we replace it with the thing that we're using, and then we go to the next one and we have to evict that, have to evict something to get that, and so forth, okay? So like row 1, row 2 also incurs N over B misses. Okay, this time they're capacity misses. Okay, we've got full associativity, so they can't be conflict misses. Okay, and it's not parallel, so there are no sharing misses. Okay, so the choices are they cold misses or are they capacity misses? Okay, at this point, they're all capacity misses. Okay, and the remaining rows are similar. So we get N over B cache misses per row. Okay, and so the total number of cache misses is theta of T times N over B, which is theta of NT over B. Okay. Now, we could at this point do tiling to minimize cache misses, but you know I don't like voodoo parameters, even though it's Halloween. Okay. So we're going to go straight to a cache-efficient solution, cache-oblivious solution, efficient cache-oblivious solution. Okay. And this strategy is based on computing the stencil within trapezoids of the space-time iteration space. Now, a trapezoid has two parallel bases, and for us, that's always going to correspond to some time step T0 and a later time step T1. And the left and right sides, which are not necessarily parallel, can each take on only one of three slopes, 0, 1, and -1. Actually, those are inverse slopes. A vertical line has slope infinity, not 0. But I'm going to call them slopes for convenience because it's hard to say inverse slope everywhere. Okay, so what I really mean is it's the inverse, or it's the slope if you were looking at, if I rotated the, transpose the axes. Okay. Now, we're going to make recursive calls on subtrapezoids whose slopes on the left and right may be 1 and -1. Okay, but the initial trapezoid, the left and right sides have slope 0. Okay. And the key property of this trapezoid, if you look at it, is that given the points on the base at T0, we can compute all the other points. Okay, so all these points can be computed. If I've got the base points here, all the other points can be computed without ever referring to the points outside the trapezoid. Okay. Now, the width of the trapezoid we're going to use is going to be the average of the lengths of its two bases. So it's the length of base 0 plus the length of base 1 over 2, and that gives us the width in the middle. So we're going to use that. Okay, it's not that important, but we're going to use that. You could have actually done it with the large n, but the math works out a little bit easier. Okay. Now, the way that we're going to compute a trapezoid, okay, is recursively. So when the recursive cache-oblivious algorithm encounters a trapezoid, and the height of the trapezoid is bigger than 1, it's going to choose one of two methods for recursively calculating all the points in the trapezoid. The first case, which I'm showing here, is when the width is at least twice the height. We call it a squat trapezoid because it's short and fat, okay? So remember that the trapezoid's width is the average of the length of the two bases. So the recursive algorithm cuts a squat trapezoid into two trapezoids with a slope, a line of slope -1 through its center. Okay, like that. Okay, we call that a space cut, and it produces two trapezoids, which it computes recursively. Okay, so we have one on the left, okay, and so this is showing that how we update things on this slide, on this trapezoid. So this trapezoid, we can update the interior points because we already have the base. That was our assumption here. Okay, so there's no problem with it going ahead and computing it. Okay. The other trapezoid we have a little bit more trouble with. Okay. And so we have to compute the left trapezoid before we compute the left one. Okay, actually, I think I left in some slides. Those were old slides. Okay, so I already showed you this. Okay, so the ones in the left trapezoid, okay, we can compute all those, but this point on the right trapezoid depends upon a point in the left one. So it's got to wait for the left one to be computed first. Another thing I want you to notice is that when we're done computing the left trapezoid, some points will have been iterated through more time than other points. For example, the points on the top base will all be iterated T1 steps, or T1 minus T0 steps, but a total of T1 steps at that point. But a point on the left or right side of this, so those guys haven't been fully iterated up to step T1. Okay. Nevertheless, it turns out, and this is pretty remarkable, we can still use our two-array scheme for storing U, because the portion of the array U that belongs to a trapezoid is computing exactly the same values as in the looping method. And like the looping algorithm, it respects the stencil dependencies. So even though things are going to be in the grid, in the bar we have, we're going to have pushed time ahead quicker in some areas than others, it's still going to be okay. We still only need two arrays. Okay, when the width is less than twice the height, that's the situation where we have a tall trapezoid. Okay, in this case, the recursive algorithm uses a time cut, okay, which is a horizontal line in time parallel to the x-axis, okay, basically through the center, and we round down, as it turns out, okay. So a time cut also produces two trapezoids, and in this case, the lower trapezoid clearly must be computed before the upper trapezoid, okay. So that's basically our recursive strategy. Okay, our base case trapezoid has height 1, okay, and that's just a loop that computes all the points on the upper base from the points on the lower base. Okay, of course, in practice, you'd coarsen the recursion and execute a base case when the height drops below some tuned constant, constant greater than 1. Okay, so here's the code. Okay, I didn't coarsen this, but I'm going to run the code and you'll and there I did coarsen. Okay, so here's the code that implements the recursion. Okay, so for this, if you start with a rectangular region, you're going to call trapezoid, okay, with dx 0, which is the slope of the left edge, and dx1, which is the slope of the right edge, is 0. Okay, and so so those are dx0 and dx1 say are all either 0, 1, or -1. Okay, and then it pretty much follows what I've outlined. Okay, pretty much follows it. Okay, the only tricky thing, okay, so the only tricky thing, okay, the only clever thing to understand is how the comparison of the width with twice the height works for determining whether to cut in space or time. And that's just a little algebra. Okay, so here I've given the formulation that does that comparison. It's not exactly, you know, the width and so forth. I didn't compute width because if you multiply it out, this is actually a comparison that you want to do. Okay, so so other than that, there's the base case. It basically just executes the kernel, and otherwise we make the comparison. Do we do a space cut? And if so, okay, we compute the middle point. Okay, and then we do the trapezoid on the left and the trapezoid on the right. And otherwise, we do a time cut. We compute the midpoint of the number of iterations to go, and then we run the trapezoid code for left and right. Okay, good. So we're gonna, so it's just a little algebra. We can still use, as you can see, the two-row technique, okay? And I want you to observe that the amount of work done in the recursive case is constant. And we'll use that fact in the analysis. So now's a good time for questions. Any questions, either in Slack or turn on your audio. Turn on your audio, turn on your video. It's nice to see people when they ask a question. Maybe you can tell me what NGL stands for, since I don't know all the abbreviations that you folks do. Not gonna lie, okay. Okay. Thank you. Okay. Okay, any questions? Is that pretty clear? Okay, so let's go on and analyze it, okay? Now the analysis is, I'm not going to prove the bound formally, but the recursion tree, if you draw it out, the sketch as I've done here, shows all the important ideas of the analysis of work and cache misses. Okay, so we're interested in the case when the problem is large and doesn't fit into cache. So n, the number of points in our grid, in our one-dimensional grid, is much bigger than the cache size m. Okay, so here's the sketch of the recursion tree, and the internal nodes each represent a constant amount of work doing bookkeeping. Okay, because if you looked at that code, okay, in fact, I'll go back and look at that code. Okay, what is it doing? It's just doing a bunch of index calculations in the interior nodes. Okay, it's only when it gets to a leaf that it actually does any work. Okay, otherwise it's just doing a little bit of calculation, okay, constant amount of calculation, and recursing. Okay, so it's theta 1 everywhere in the internal nodes. Okay, then the bottom, when we're analyzing the, I'm going to draw the recursion tree for the caching case, even though we'll do work at the same time, kind of. okay? So the bottom of a leaf trapezoid just fits into the cache, okay? So that means its parent didn't fit into the cache, okay, but it did. So it's got to be about the same, the base there has to be about the same as the base of its parent. And so they straddle M. So W therefore is theta M, okay, because W and like say 2W are, you know, W is less, 2W is more, that's theta M, okay? Then the leaf trapezoid contains H, so H is the number of iterations it has to do in time, and W is, as we say, the length of the bottom that just fits into cache, okay, which is W squared points, okay? And the reason it's W squared is that the height of the leaf trapezoids are about the same size as the bottoms of the trapezoids, because we're always cutting the larger dimension, okay, of any of the, you know, internal node trapezoids, any of the big trapezoids. So since we always cut the larger dimension, you end up, you know, getting down to something that has a good aspect ratio, has a bounded aspect ratio. So they're about the same size. So therefore, each leaf trapezoid contains theta W squared points. And then if you think about it, okay, the recursion may continue to the bottom, but it's only going to take W squared work to compute because all the work is in the leaves, and we compute each leaf once. Okay. Once the bottom of the trapezoid fits into cache, the calculation of that trapezoid proceeds with no cache misses other than those needed to bring the bottom alone into the cache. Okay, so you bring the bottom in, okay, and that's all we have to do. And since a trapezoid's bottom is contiguous in memory, the segment caching lemma says that it takes order W over B misses to read it into cache. Okay, so that's how many it takes, and it's doing, but notice this, it's doing W squared work. That's really good. Okay, that's really good that we're doing a lot of work, but we're having relatively few cache misses. Okay. Now there are NT points overall. Okay, that's what we said was in our iteration space. And each base case trapezoid we've just argued contains theta HW or theta W squared, either way. Okay, and every point belongs to some base case trapezoid. Okay, because I haven't made a mistake in coding and left somebody, you know, left a grid point out. So that means there are theta NT over HW trapezoids, because they each have theta NT over HW size, okay? And there's NT overall, so the trapezoid partitions into, you know, the leaves. The leaves are all a partition of the iteration space, and we have therefore NT over W squared leaves. And the number of internal nodes, by the way, is just this is approximately the same, because the number of internal nodes in a full binary tree is one less than the number of leaves. So that's practically the same as well. Okay, now, so since the number of internal nodes, you know, is one less than the number of leaves, and each contributes just a constant amount of work, okay, and if it's a constant amount of work, it's got to be a constant number of cache misses, okay? So, so the internal nodes are actually not doing, you know, they only do constant work, and so, so the the work and the cache misses for the internal nodes is therefore order NT over W squared, okay? Because that's how many we have, and they each cost us about a constant, okay? Whereas, so that turns out they don't contribute significantly either to the work or to the cache misses. All the stuff that's going on is in the leaves, okay, in these base case trapezoids, okay? So, whoops, I missed one here. Got those switched, okay. So the work is just the number of leaves times the work for each leaf, which is NT over W squared times theta W squared. Well, that's just theta NT. So no surprise there. The work is going to be the same as the looping algorithm. We're computing on each point once, and you've got a tree that's got constant size in the nodes, so it's not contributing anything compared to the leaves. But we get a big savings in cache misses, okay? The number of cache misses is the number of leaves times the cache misses for each leaf, which is theta of NT over W squared times then the, I said this, times the cache misses for each leaf, okay? And that's theta W squared. Sorry, that's theta of W over B. That's this one. Okay, each leaf incurs W over B. So you multiply that through, you get theta NT over BW. And W, we said right from the beginning here, is theta M. So we get theta NT over BM. That's a huge savings in cache misses. It's a factor of B times M, okay? I mean, really big, okay? Really big. And for a big cache, it's like, whoa, that's an amazingly small reduction in the number of cache misses. Now, in higher dimensions, the savings are less, okay? So in 2 dimensions, you save a factor of square root of B square root of M rather than BM. And in 3 dimensions, the savings is B times the cube root of M. Okay, so you can see that the savings are diminishing with dimension. And in general, for D dimensions, the savings are B times M to the 1 over D. Okay, and it turns out these bounds are optimal. Okay, any questions? Does this algorithm actually run faster in practice? We're going to do that. We're going to do that and see whether it does. Okay. Any other questions there? So wasn't it NT over B misses before? Yes. It was NT over B before. But here it's B, you know, we're getting an extra factor in the denominator of M, right? Because essentially, as you go down the tree, eventually a trapezoid fits into cache. Okay, just because we're cutting it down, now it fits into cache, and then we can do essentially M squared work, okay, the cache size squared work, while paying only the cache size divided by B cache misses. Okay, so that's huge. Okay, just whoop. Now you could get the same effect by tiling things of that size, but then, okay, you would have to keep your code tuned all the time. You'd have this tuning parameter, and if you got it wrong, it could be worse than not having tuned it at all sometimes. Okay. And why is the number of cache misses per leaf W over B? The reason that it's W over B is there's only 2 arrays. That iteration space we don't really have. We just use 2 arrays. We keep a given row and the row above it. Okay, so once you bring those into cache, okay? That takes you W over B or W over B cache misses. Once you bring those into cache, you keep computing up the trapezoid and there are no more misses, okay? Because initially only the base has to do it. So I showed you the iteration in time, okay? But that's not real, okay? That's just, okay, so let's have some fun. I want to show you a simulation. We're going to race the divide and conquer algorithm against the looping algorithm. And we have a 3-point stencil we want to compute. And the simulation I'm going to do is going to go for 87 steps on a one-dimensional grid of 95 points. And our ideal cache with LRU replacement can fit 4 points per cache line. And it has room for 32 points on 8 cache lines. So it's not a big cache, but it's going to illustrate the idea. And I'm going to run the two simulations side by side. Teal is which is bluish green, is a cache hit, which costs only 1 cycle. And magenta, the purplish red, is a cache miss, which costs 10 cycles. And so now I'm going to stop sharing for a moment while I get the simulation set up. Okay, so how do I stop sharing? It's way over here. Stop share. Okay, let me start up okay, this is the stencil sim. Okay, now I'm going to do this. Okay, and let me share this. I need to go back to Zoom. How do I get back to Zoom? And do share screen. And there it is. Okay, so here are my two simulations here. Okay, and I'm not quite sure why it blanked out there just as I did that. I hope everybody can see that. So, so let's start running the two simulations. Are they running?
I think you have to press G to start, right? I don't see anything running.
Oh, there we go. Okay, so on the right, we have the Cache-oblivious code, and on the left, we have, I'm going to speed this up a little bit. Okay. So you can see on the left, we're taking a cache miss every single time. And I can toggle the display of cuts. So these are the cuts that the algorithm is doing. So it finishes the lower, that was a space cut there. And then it does a bunch of time cuts to get down to something that it can operate on. Okay. So the Cache-oblivious stencil wins in theory and it wins in simulation. Okay, we'll speed this up a little bit. Okay, so everybody see that? Okay, so the magenta, those are the cache misses. And you can see once it gets down, even though it's doing divide and conquer deeper, once it gets down to a trapezoid that is smaller than the cache size, okay, which is 32, okay, 32 points, it doesn't take another cache miss. Okay. Okay. So let me quit this and go back to PowerPoint. There we go. Okay, so we're back. Okay, now we're going to have a little bit of fun. I'm going to try something more daring, which is I'm going to try to do a live demo of a two-dimensional heat equation on my MacBook Pro laptop, which has 8 cores. Okay, this calculation requires a 5-point stencil, and I'm going to compute it on a 300 by 300 image, which contains, therefore, 2 copies of 90,000 doubles. And we're going to measure how many frames per second each of the 2 codes can sustain. And I'll switch between the divide and conquer cache-oblivious code and the looping code. So while I get set up, let's do a poll for how much faster you think the divide and conquer will run, how much faster divide and conquer is than looping on a real machine. Okay. So let me stop the share. Let me. Do this. Okay, let me share that if I can. Okay, can people see this? So this is the serial loop algorithm. I know that the printing is small. I couldn't figure out how to make it be bigger because I'm no expert on glut, which is what this is using. Okay, can people read that? So basically it's saying right now it's running about 1,300 frames per second. Okay, so it's able to update that whole array 1,300 times in a second. Okay, so now let's try the and why don't we make this kind of interesting by having a heat source? Okay, so let me just see here. There we go. There's a heat source. Okay, and I can move it around. Okay, and you can see that it diffuses. And I can even make the heat be negative. Okay, and so forth. Okay, and while we're doing this, it's getting now about 1,100. Okay, and I think that's because I'm running so many other things. So it's slowing down because I did not quiesce this machine. Okay, so now let me switch to the cache-oblivious version. Okay, so there's the cache-oblivious one running about 1,300. Okay. And now I'll switch back to the looping version. Okay. Just over 1,000, maybe almost 1,100. There it is up at 13. So how many people guessed that it would run just 10 or 20% faster? Nobody. Okay. Yeah, isn't that amazing? That's because there's so much in the hardware built to support loops. And latency, you know, they do prefetching and they do all kinds of things, okay?
The memory bandwidth is also over-provisioned if you're only using 1 core.
And the memory bandwidth is only provisioned if you're, well, that's what we're going to get to. You're trying to steal my thunder, okay?
Sorry.
Okay. So let's go back to PowerPoint. Okay. So how can the cache-oblivious trapezoid decomposition have so many fewer cache misses, but the advantage gained over the looping version is so marginal? Okay. So it turns out that prefetching helps a lot. Okay. The code really can be processed, and the although there's latency, the bandwidth is not saturated. Okay, prefetching can, it's very predictable. It prefetches the stuff so it doesn't miss in the cache. Okay, it's already been prefetched. Okay, now it turns out that it takes bandwidth for prefetching, and it's a lot more energy than for the looping code. Okay, so so in any case, there tends to be plenty of bandwidth for one core. Okay, so now let's take a look at a parallel solution. Oh, darn, I'm going to run over again. Okay, so this is the slide that I discussed, distributed on Canvas with Tuesday lecture slides, but we didn't go through it, and I'm only repeating it here for convention. There's only a little bit known about the caching behavior of parallel algorithms. And this particular theorem says that you can bound the P processor. If you look at what this says, it says you can bound the P processor number of cache misses by the one processor plus this term, which has to do with how many successful steals, how many migrations you have to do, times the size in cache lines of the cache. Okay, it's not a very strong bound because M over B tends to be large, and S sub P is the total number of successful steals, okay, which could also be large. But real programs don't seem to come close to this order SPM over B upper bound. And it's an interesting research problem to find a bound that's better. But the theorem does say, and this is the bottom line, that minimizing cache misses in the serial projection minimizes them in parallel executions. And it does seem like a good idea to do in practice. So if we go to parallelize this cache-oblivious algorithm, well, the first thing we look at is time cuts, and there's no way to parallelize it. The bottom trapezoid has to be computed before the top one. Okay, so there, no luck. Okay. Well, space cuts don't parallelize either. Okay. You've got to traverse this trapezoid on the left before you can traverse the trapezoid on the right, because the right one is dependent on the left one. Well, it turns out that's not quite true. We can come up with a different scheme for a space cut. And the idea there is that was an old slide. A parallel space cut produces, you can do as a V cut out of the trapezoid. And it produces two black trapezoids that can be executed in parallel, and a third gray trapezoid that must execute in series with the black after the black trapezoids. Okay. Now, in this case, we're going to get some trapezoids that are upside down. Okay. And so for an inverted trapezoid, though, you can do the same thing. You can do a parallel space cut that cuts a wedge into the trapezoid, where now you have a gray trapezoid that has to be computed first, but after that, you can compute the two black trapezoids the same way, and the time cut is the same. Okay, so let's take a look at the heat demo with parallel execution. Okay, and this is a silk code. Let me end stop share and share screen. let's see. And I want to go back to where's my, oh, I see, I stopped it. Okay, that was wise of me. Okay, so now I want to share the desktop. Try that again, they don't update. So let's go back to Zoom and try to share this. Okay, and now get the tense dome again. Okay, share. Okay, so let's heat this up a little bit. So now we're running the serial loops. Okay, and we're updating at about 1100 frames per second, a little bit more. Okay, so let's run parallel loops. Okay, so there on 8 cores, we're running about just under 1600 frames. So serial. Okay, now we're running under 1000. That's because we heated it up by running more computation, and DVFS is probably kicking in. Okay, so there's the serial, and here's the parallel. Okay, oops, sorry, parallel. There's the parallel. So we're getting about 1.5 times faster on 8 cores with the parallel. And this is definitely because we're bottlenecked. Okay, so let's go back to the serial cache-oblivious one. So that's still running faster than the serial loops. Here's the cache-oblivious. Here's the loops. Okay, here's the cache-oblivious. Now let's parallelize that. Okay, wow. Now we're going 4,000, okay, which is really quite substantial. And I'm just going to run top here for a second and see what's going on. Yeah, Zoom's taken up a lot, and some other stuff is taken up a lot. So that's why we're... so in any case, I've lost my my heat. There we go. Okay, so here we are, the parallel cache-oblivious. That's just tracking. That's doing great at around 4,000. I had it running almost 8,000 earlier today. Okay, and then so the frames per second, and then if we go back to serial, what we really want to compare is that's the parallel. We want to compare with loops. Here's the parallel loops around 1100, and the cache-oblivious here is around, at this point, around almost 4,000. Okay, so clearly we're getting hampered by DVFS, and probably some other stuff because I didn't quiesce. This is just my laptop, but you can see the effect. Okay, let me quit here. Okay, and start up and just finish off the lecture. I'm almost done here. Share to Microsoft PowerPoint. Okay. And in fact, we've run this on some really big problems. Okay. 3,000 by 3,000 grid. Okay, for 1,000 time steps on 4 processor cores. And we get about a 2x speed up on the serial. So there's a 2x speed up on on the looping, whereas we get like a 4x speed up, and we're a lot less to begin with. Okay. And so what's going on here is that the memory is the bottleneck. And so here, just to close, and I just have a few more words, sorry to be running over. There are typically 4 impediments to speed up. Okay. Insufficient parallelism, scheduling overhead, lack of memory bandwidth, and contention, either lock contention or true and false sharing, which is a contention problem as well. Okay. And I've ordered them by the most often to the least often issue. Usually when there isn't speed up, it's because somebody doesn't have enough parallelism. And then if they have enough parallelism, it's usually because they have scheduling overhead. And then if neither of those is the problem, it's usually the lack of memory bandwidth. And finally, if it's none of those 3, it's probably contention. Okay. So now how do we go after these impediments? So you know that Silk Scale can diagnose the first 2 problems, right? It gives you a measure of the parallelism. So you know whether you're trying to, whether you have enough parallelism in your algorithm to be able to get good behavior out of a scheduler. Okay, it also computes this thing called burden band, which will tell you whether or not you have scheduling overhead. Okay, by saying, look, it's going to be very expensive to move things around. Okay. And so it can help diagnose the first 2 problems. And that's pretty easy. Okay, easy to run those things. Okay. But how can we diagnose a lack of memory bandwidth? Okay. Now, there's actually a bunch of ways. One strategy that I don't generally recommend, but which one of my students did, was to open up the hardware and take out all the memory chips but one. And then he ran the code. Okay. And since one processing core usually can't saturate memory bandwidth, the serial projection doesn't really slow down at all. Okay. But when it only uses one memory bank. But the parallel code, you get to the bottleneck on the memory system very quickly if you only have one memory bank. Okay, so he was able to diagnose, oh yeah, I've got a memory problem that way. Okay, but that's kind of thing. So there's another strategy which sometimes works that doesn't require you to void your warranty. Okay, and that is to run p identical copies of the serial projection in parallel. Okay, if you have enough memory to do it, that tends to be the limiting factor. Okay, so, but if sometimes you can isolate part of your code, you can do that. So if when you run one version, okay, it runs fine, but when you run p identical versions, they're all going to go to the memory. And if it's a problem in parallel, it will be a problem for this sort of obviously parallel thing. You just run p copies, one on each core, and see whether or not it saturates the memory bandwidth, it slows down. Now, diagnosing lock contention is hard. Okay, it's doubly hard to detect the potential for lock contention. Okay, if you're programming in Silk and writing deterministic code, it's something you don't have to worry about much. Okay, but if you're running non-deterministic code or you're in another environment such as pthread, it's hard. So as you know, the Open Silk runtime system is written in pthreads. And so we frequently have this kind of problem to diagnose, okay? But the idea of the Open Silk project is to tackle the hard problems so that Silk programmers don't have to. And even harder than lock contention is detecting true and false sharing. So as I say, if you're running a deterministic code in Silk and using a good memory allocator, your risk of this kind of problem goes way down, but it's not zero. But before you waste your time trying to diagnose the potential for lock contention or a sharing problem, you probably want to eliminate the first three reasons. It's the least likely explanation for lack of speed up, and it's hard to diagnose. And I find it really interesting that when you order these 4 problems by frequency of occurrence, as I've done, it turns out you're also ordering them by ease of diagnosis. Very curious. I'm not sure why that is. Why isn't the one that is happens the most, the hardest one to diagnose, but it isn't. Okay, so I have slides here in cache-oblivious sorting. I didn't prepare them. I'm not going to present them. But you should know, however, that there are asymptotically optimal cache-oblivious sorting algorithms. And I've lectured this material in the past, and I'll include them in the lecture slides I post in Canvas, but I'll warn you that I haven't revised them for this year. Okay. This is a little bit of what the cache-oblivious sorting algorithm looks like. It's called funnel sort, and it's got a bizarre divide and conquer. Okay, but it's optimal. And here's a picture of how it works. It works to merge. So there are a lot of other cache-oblivious algorithms, and a really interesting area is in the area of cache-oblivious data structures, which has turned out to be a huge area. Okay, and that is by, for example, cache-oblivious B trees make database and file system code robust to hardware parameters, such as disk page cache and disk cache size and memory buffer size and so forth. So the concept of cache-obliviousness is really vital. And that completes my lecture. I'm sorry to have run over again, goodness. And please, if you're still around, please vote on Tuesday if you've not already, and it's legal for you to vote in the United States, and wear a mask. And I'm happy to open it up and take a few questions.